I was wondering how many people would find this interesting, but I was told on Friday night that there's probably a spurious correlation between people who enjoy Python and data science and people who enjoy mobile games. So it's a pretty good thing there. So I'm Andrew Patterson. I'm a data scientist at Natural Motion. I actually lead all the analytics and data science for one of our games, Dawn of Titans. But this is kind of these are the kind of games that we've got. So Dawn of Titans is kind of a mid-core game where you kind of battle it's like a social battling game. So you're building a city, upgrading your troops, upgrading these Titans, battling each other and trying to basically just win the game. And CSR2 is more of a racing game, so you're doing a similar thing, but you're upgrading your cars and then you're racing against your friends and things like that. We have the CSR franchise, which obviously CSR2 has been built on, and then we have some other smaller games that kind of we started out with. I would implore you all to download Clumsy Ninja because it's fun, really fun. So I'm going to talk to you about how we deal with cheaters, specifically with Dawn of Titans, but actually this whole concept has happened across Dawn of Titans and CSR2. They are obviously, in social games, a huge issue because it's not just that they are cheating us, they're actually cheating the other players that are playing the game. First, I want to just go through quickly the free-to-play model. I think everyone understands most mobile games now are in this free-to-play model, which is great because we can get our games into the hands of as many people as possible who have a good enough device to play them. But it comes with a problem. So with no context, does anybody understand what this percentage might be?
Wales?
Yeah, well, not necessarily Wales, but this is actually just the percentage of people who convert in free-to-play games. So it's, I mean, amazingly, we have a huge user base of playing, but a very small amount of people that actually give us revenue. As a business, we still need to make money, and actually that only comes from about 2% of our players. So if we're thinking about detecting cheaters in that game, it's a real problematic thing because if we're thinking about them as outliers in the data that we're looking at, actually 100% of our revenue is also coming from outliers. So it's it comes to it's a problem that we have. So I'm going to quickly talk through just quickly what you would cheat in a game. This is Dawn of Titans. This is my Dawn of Titans on my mobile. I'm Crash Kid, only level 4. Started on a new mobile recently. So a lot of the games have. A lot of the games have currencies in the game, so obviously that's a really obvious area that you'd hack the game, give yourself more currency to do things, buy things in the game, things like that. Particularly gems, which is kind of a hard currency. That's where your skip weights come from, like skipping through the game comes from, and basically buying some of the bigger items. And this is where kind of our IAPs are attached. We have VP, which is a social currency, and so what you use that for is whenever you battle somebody, you get more VP, you rise up the ranks, get rewards and things like that. And then there's loads of other things like your actual general player profile, which gives you extra rewards and things like that. So I just want to show you this for a second because here this is the kind of social map in our game. And we've got Carlos8915 here. Now, is he a cheater? As a player, I don't perceive him as a cheater. He looks very similar to me. He's got a few more lands, but he looks very similar to me. Now, he could be cheating, but this isn't necessarily the problem. Like, I actually don't mind if I don't really care if he has ways of nominally cheating in our game because it's not really affecting me. Like, I'm not perceiving him to have to be better than me because of that. I'm not saying, hey, how is he upgrading himself so quickly when he's obviously a cheater, and I'm going to, as a player, not like the game because of it. And so what we're trying to do is we don't have to care about all of the cheats in the game. We actually just want to care about the player-facing ones, the ones that are really going to affect other players in the game. So just going to quickly run through, from an engineering level, how people cheat. So these games are always online. So they're always talking to the game server. Every transaction you do, every kind of button click you do, we're talking to the game server. So from a client side, there's the obvious hacks. You can actually download hacked builds off online. This is not one of our games, so I'm not going to show you the APKs for our own games. This one's for Clash Royale. Please don't download that one either. And then these already have it's basically the easiest way. They're pre-configured, so you'll have loads of gems to play. You might even just start at a higher level, and it's effectively you haven't spent any money and you can just rule the game. These are actually generally quite easy to stop. There's also these assistant applications, so you could have a completely fine game on your mobile and use an assistant application to just change values in our metadata. And this is a harder problem because actually people generally do it in smaller increments. Like just when they need it, they'll change the value, and so you know, from us looking through the data, you may look quite normal, but actually you're kind of you're just edging there with your cheating. There's also like network edits, which is really, really tough. So your client can be completely fine, and the transaction that's sent to the server is then just captured, and you can then edit that. So you don't even need to be online at this point. People can actually just capture these capture these kind of transactions and then just send them to the server. Obviously, the server is robust enough to understand most of them, but this is an arms race. Like every time we find a way to stop something, some clever clogs finds a new way to do it. So it's a constant arms race, and this is why, rather than dealing with it from an engineering point of view, which we do, we also need to double down on kind of catching users within game. So this is where it comes from an outlier detection problem. So as the transactions come in, the easiest thing to do, which is a lot of the ways that we deal with cheaters, is just deal it from a transaction level. So this transaction has changed our currency by X amount, and you know whether that was an outlier or not. But as I've said, like a lot of the time, it's just scope creep. It's like creeping, cheating. So actually what we need to do is aggregate the user level data to kind of understand over time how big a difference have they made than we were expecting them to do. So I'm going to walk through some kind of different ways that we've dealt with, you know, cheating as an outlier detection problem. Start from the simplest approach and really just move forward with that. So obviously, we've got single variate solutions. So if you look here, we've kind of got battle win ratios here, or player progression on your first day. In terms of the mathematics, there's something called kurtosis, which is a really simple thing. It's just really the amount of tail that you have on your distribution. It's easy to assume that high kurtosis means that this variable has a lot of outliers compared to your normally distributed data. And so we can kind of use that to understand what variables perceive as outliers versus not. So you can see here for player progression, there's a huge long tail here. So it's very easy to expect that, you know, these are huge outliers here. And it's not possible to get to some of these levels on your first day. So we know straight away that these people are cheating. And so it's a really, really simple method. And in fact, actually, we don't necessarily need to do some deep level data science here. We can just put in theoretical maximums and say you can't, you know, it's not possible for you to get here. Whereas actually with the battle win ratios, it's a bit harder. Like you could be winning a hell of a lot of battles compared to what you should be doing, but there's more nuances and more issues there. So if we look at it from a multivariate solution, you can obviously see that the battle win ratios may be affected by the troops that you take into the game. So obviously that's quite correlated, but there's still going to be outliers there. So we've created, in a single variate, we've created a distance metric from our kind of average, our mean. So how do we do that in the multivariate sense? It's not just a kind of Euclidean distance. So what we want to do is create that ellipsoid around so that we can kind of understand that this is an outlier just as this is an outlier, even though, for example, they are actually very, very different in terms of distance from the average point of our data. And what we use is the Mahalanobis distance. And what this is doing is really just creating a similar distance metric, but taking into account the variance of each of the variables. The easiest way to think about that is if we, on the two-dimensional space, if we actually just took a simple principal component. So in fact, actually, we've just scaled down our variance, not necessarily the fact that they're non-correlated, that doesn't really matter here, but the fact that we scale down our variance means that it's now just a simple kind of Euclidean distance around that space. So that projection, if you think about the Mahalanobis distance, it's basically just a Euclidean distance in a kind of projection, a scale invariant projection. Cool. So, yeah. So, okay, back to the problem. Are these cheaters? I mean, we've got people who are winning a lot of battles, but they've also got a high troop score. Maybe the troop score is the problem, the thing. But you've actually also got outliers here that are just people who are really bad. Like, they're not very good at this game. So this is the thing. Like, whenever we do, as we're going through this, it's like outliers doesn't equal cheaters at all. It's actually just, so we need to be really, really careful on what we're actually detecting as an outlier and what we're actually pushing through as a potential cheater in the game. There's also a notion on this. So this is really nice because you can obviously see that there's outliers kind of completely around the distribution. So even if we calculated the ellipsoid, the mean is probably, even if we take some of those outliers out, that mean is probably going to be in a similar place. So we can kind of properly understand that ellipsoid, not necessarily having to worry about the outliers. This is a really, I've actually just nicked this straight from the scikit-learn website, but only because it is the simplest approach, simplest kind of graphical representation of the importance of kind of understanding a robust measurement of that kind of ellipsoid around your distributions. So if you took actually an ellipsoid and included those outliers, it's going to be very, very highly skewed. So what you need to do is kind of understand what that ellipsoid might look like through kind of samples of your data such that you're trying to take out those outliers and try and get a good graphical representation. So the mean of this ellipsoid is not necessarily the mean of your data. It's actually the mean of kind of your non-outlier data, your inliers. You can use two approaches for that. There's the minimum covariance determinant, which is actually in scikit-learn. There's also the minimum volume ellipsoid, which is a slightly more robust mechanism. But effectively, the minimum covariance determinant is kind of a direct calculation. Minimum volume ellipsoid is an iterative method where actually what we're going to do is just sample smaller sets of our data, calculate an ellipsoid that covers a certain amount of our data points, and then just take the smallest one, so the one with the least outliers in it. That's a kind of an iterative calculation of what our kind of mean and the covariance of our data could be. So just skipping back, this works well for normal unimodal data. But as you go to higher dimensions, this is not necessarily what you're going to see. And so we need to kind of abstract this and think about a different way of doing it. So rather than a distance measure, I'm going to kind of show you an error measure. And what we're going to do is use neural nets. So I'm guessing you've probably seen a picture like this about 10 times this weekend. So what we're going to do is actually just create a really, really simple neural net, which is going to take our input vector of our data of our users, and we're going to learn the kind of structure of this data and output and try and basically replicate that data from a lower dimension, similar to what you'd see as maybe an autoencoder. The reason this is good for outliers is actually, as it learns the structure of the data, any variable any kind of sample that we put into the neural net that doesn't actually fit that structure is going to be really, really bad at predicting that data. So in fact, actually what we can do is create an outlier factor or an outlier score similar to the distance metric, but actually it's just an error metric of, we've built a neural net to understand the structure of our data. But as you put a sample through and it's never seen before, it's not going to be able to predict it, and therefore it is an outlier based on kind of what our data normally looks like. So it's reasonable to assume that the way that this works is you want to represent your data in a lower dimension, so you don't want to actually 100% replicate your data, you just want to kind of estimate it. It's reasonable to assume though that neural nets, you can optimize a neural net very, very well to the point where even if you take a sample of your data and maybe it has one or two of your outliers in it, even if it has a couple of samples, it's probably going to try and understand, there's a good chance it may understand the structure of that data. And so actually you might find true outliers in your data not having a huge outlier factor. So what we kind of do with this replicated neural net is from the paper directly, there's a activation function which effectively just creates a step function. So rather than this middle hidden layer having a fully continuous output, it could take any value. We're actually only going to give it a certain set of values. So we're effectively just clustering our data down into this hidden layer. So for example, here we've got 3 inputs. And effectively what we're saying, of 3 continuous variables, but we're effectively going to try and represent that as just 2 neurons, 4 steps, 8 bits of data. And then our net is going to kind of try and predict out that data again, and there's going to be an outlier factor based on kind of how badly we did. So there's a big problem with this in an implementation standpoint. This completely makes sense for outlier prediction from a theoretical standpoint, but from a kind of actually implementing this is really tough. These step functions, if you're, for example, training your neural net on kind of gradient descent, it's not possible to move through this activation function because if you differentiate these values, they're all just 0 on those kind of flat planes. So in practice, what we actually did is just kind of relax these conditions and bring it back to a continuous variable, which is, you're probably thinking, you've just talked about how important this is and you've just thrown it away now. But it's an important thing to just note, because we can still use this continuous distribution for the continuous activation function. But given that we know the problems with it, it means that we just make sure that when we're training it, we kind of have a very, very early stopping criteria. And in practice, like when we actually did this, we probably had a very, very early stopping criteria because we actually had a lot of false positives in terms of what we thought were outliers. But it was, but we found that this was probably the best approach. This was definitely the best approach. And going back to this versus the distributions, is we were able to feed it much different data, and kind of bimodal data or very, very highly skewed data, and it dealt with it very, very well. So that's kind of a whirlwind go through outlier detection. So let's just touch on a few other points of just kind of the whole process. So before we even put it into the outlier detection system, like whatever model we use, how do we deal with variable selection when we're talking about outliers? It's not a simple cut and dry process. You do a classification, you're just going to kind of take the mutual information of each, like a very, very simple approach is just take the mutual information of each variable and you take your top X variables and run that through your model, or that top X just being a hyperparameter to kind of optimize. But in kind of outlier detection, particularly outlier detection trying to find cheaters, we can't necessarily just take variables that have a high difference between their inliers and outliers. So this is one way you can do it. You can actually algorithmically understand this is by taking a variable with a high kurtosis, knowing that the difference between your outliers and your inliers are very, very high. But you can't necessarily do that in practice because your outliers are not necessarily definitely the things you want to find. They're just a medium to find some of them, basically. So with the variable selection, you still have to be very, very intuitive, and you still have to craft these variables, which obviously you're adding bias to your own kind of model here, but there's not really a foolproof way, or if there is, I'd love to speak to anybody who knows a foolproof way of doing it. So you still have to kind of really, really manually craft these variables to make sure that they are going to give you actual cheaters rather than just outliers. So once we've got our outliers, what do we actually do with them? We actually kind of need a ground truth. So we work with, and again, there's no easy win here. Unfortunately, we have to go through a sample of our data and just understand what a cheater looks like versus a non-cheater. We know that these outliers that we found are most probably our cheaters, but there are going to be a lot of false positives there. There's going to be high spenders, then there's just going to be people who are very, very good at our game who have found kind of completely legitimate ways through. The problem with that also is there's kind of a needle in the haystack problem. If we just sample down our data and we've only got a 1% outlier thing, there's only going to be a few people that are outliers. So we're only going to know a little bit about them. And then we'll have a load of other people that we don't see as outliers who are probably not cheaters. And we're not going to see anything in between either. So if we look at the variables, we're not going to see the tipping point in which people are a cheater or a non-cheater. So really, really simple way of dealing with this is just resampling the data based on the actual outlier score, the distance score or the error score that we found from the neural net. And that means we get a really, really good representation across the board of outliers, inliers, and everything in between. And we can really, really understand the nuances and the tipping points between who's a cheater and who's not, which is awesome. And I mean, it's a bit of hard work. It took me a few days of just a lot of coffee going through a lot of variables at this point. But we kind of had a labeled data set at that point, which we can kind of analyze and model, and we have kind of a ground truth of who are cheaters and who aren't. So in terms of, just quickly, so 2 examples here of what we did actually after it. There's 2 games, CSR2 and Dawn of Titans, and they actually diverged in what we did after this. So one of the games actually, after going through that process, we actually only found a finite amount of ways that people were able to cheat the game. And so we kind of took a step back and was like, well, we could obviously just create a classifier here, but given the fact that our ground truth is only 8 facts about cheaters, we can in fact just create very, very simple heuristics on those 8 facts. And building a model on top of those is ridiculous, because it's never going to be as good as those 8 facts that we found for that ground truth. So in fact, we just create very, very simple single variate heuristics off that data. Another game actually had much more nuances, and there's a lot of very, very small ways that people were cheating, in such a way that we weren't going to be able to just craft a rule for each one of those. So in fact, we actually just used our labeled data set to build a classifier to classify who was a cheater, who wasn't. And that's kind of how we output that. I'm not going to kind of go into that because this was more about kind of the outlier detection method. But in practice, that's kind of what you end up doing with your ground truth of data once you've found those scores. Cool. So a little bit early. So summary. The fact was to find and ban the cheaters. There's obviously issues with that. We're never going to be able to just find cheaters, because actually all of our really, really high value players look exactly the same as them. So we were never going to be able to do this in a simple way. So there's always going to be a lot of handcrafting involved. But we kind of use these outlier detection methods to try and pinpoint actual potential cheaters and potential high value players, such that we can understand them better, build models and build infrastructure so that we can remove players and kind of let people enjoy the game the way they should, and not feel like they're getting the short stick of the game. So kind of using intuitive variables, detecting the outliers kind of either through very, very simple mechanisms, or actually using kind of neural nets to do so. And then there was a kind of like rank set resampling that we used to get a good view of what an outlier looks like versus not, and everything in between. And that everything in between was the most important bit, because we really needed to understand the tipping points. So after that, we kind of just, we've now got a ground truth, and it's just an exercise of either building a classifier off it, or creating new heuristics. So that's kind of the journey that we took through data science, using data science to kind of find cheaters in our game. Has anybody got any questions? Oh, sorry, no, quickly. I knew that there was one more. So just quickly, you can actually just find all of these stuff really easy. So scikit-learn's got loads of packages, especially the elliptic envelope and minimum covariance determinant. The minimum volume ellipsoid, there's a implementation on GitHub by Joe Ernst, one of our old analysts. And the replicated neural net doesn't currently have an open source thing, but if you're actually thinking about the relaxed version of what we built, it's actually a very, very simple feed-forward neural net. So you can kind of build that either through TensorFlow on your own, or actually there's a very, very simple classifier that they've built through TensorFlow to build that, which is quite good. So yeah, questions? Go on.
So let's just say I get your game and I write a pod that plays your game, and I'm a cheater. But I only do it maybe 15 minutes a day or 30 minutes a day or something, so I don't progress that much. Then I would just look like an average player, but I will still be cheating. So that's going to make me impossible to do that?
It will, but is that necessarily an issue? I think I kind of broached on it earlier on in the presentation, is actually if we can't necessarily detect you, can our users realize you're a cheater? Because that's the only thing that we actually care about. We don't generally someone who's going to cheat in our game, we're not going to be able to slap them on the hand and say, don't cheat again, and they won't cheat again, and they might then spend in our game. It's not going to. It doesn't do that. So we can either try and find absolutely everybody, or actually we just want to focus on what is detrimental to our game, and the detrimental part is actually just what you can perceive as cheating, and that's the bit that one of the biggest kind of points away from this is actually like the perception of cheating in the game over actually what cheaters there are. I think that was one. Sorry, gone.
Do you ever get situations where your algorithm labels someone as a cheater and you ban them, and they come back and test their innocence? How do you do that?
We do. So the way that we actually build the kind of end process is it's not a completely, we don't just completely automate it. There's certain levels of it. If we build very, very simple heuristics of facts of like this is a cheater, we can kind of automate it. But there's a lot of levels of kind of, well, there's a grey area here, and it goes to our support team to kind of make a decision. If people come back and we are, so that kind of rules out necessarily the kind of the false positive of banning somebody. But if they come back, we kind of have to just say, you're banned. We can't tell them why, because they'll just learn how they're banned. They'll learn the constructs that we've put together to stop them. And so it's a case of just not really talking to them. It's kind of just like, I'm sorry, you were banned because we found that you were cheating our game, but we can't necessarily tell them why, because then they'll just find new ways to do it. It's that similar arms race. So what we're trying to do is stop the arms race by not telling them exactly, not showing them everything.
When you're training the neural net, what was the target variable?
So the target variable is actually the data itself. So what we're trying to do is, so what this neural net is doing is it's not trying to predict whether someone's a cheater or not. We're just taking our data, so our say for example our 3 data points that we know of a user, and we're running it through a model such that we're optimizing this neural net such that this neural net can predict our input data really, really well. So any normal so it's going to learn the structure of the data. Any normal data, there'll be a very, very low error to it, and any outlier data, which the neural net doesn't necessarily know, is going to then come out with a very, very high error rate, and that's what we use as a kind of outlier factor.
So it's that's why you said auto.
Yeah, it's kind of yeah. So the replicator neural net is the theoretical replicator neural net is using the step function inside, but actually we've relaxed the assumption, so effectively we're using an autoencoder for a slightly different purpose.
Hi, thanks for the great presentation. When you were exploring the data, could you think of potentially good triggers or thresholds to differentiate between potential cheaters or spenders?
Yeah, there are. So, I mean, the first thing to think about is like, hey, I mean, we're talking about spenders here. We've got a piece of data in the fact that they've spent. And so it's kind of a naive thing to assume that we could probably just use that very, very easily. But there's a lot of nuances in between. For a fact that there's actually people who decide to spend in our game and then they go on to cheat. And so we need to kind of, we can find ways in which we can kind of separate them out, but actually we kind of have to treat them as similar because they are similar behaving players.
Are there any reasonable thresholds between, or more obvious ways of differentiating between the two categories?
There is. I don't know whether I can give that away. So there's certain things, yeah, sorry. But it's a good question. There are different ways that we can do it, but I can't really go into it. So, okay. I think, go on, right at the back.
So thank you very much for the talk. I probably have 2 quick questions. First one, like I think that it might be not a data science issue, but more software development issue. Like in game of chess or poker, you just cannot replace the metadata and say that you have 2 aces or you have 2 queens on your board. So it might seem for me that if game has rules, you might really solve it without the exercise, just having some SSL like authentications or some coding encryption or some other stuff. Second one, about distances. If you had some sets with categorical and numerical variables, how would you think about distance between these samples if you have kind of combinations of both?
So the first question about the software engineering problem. So yeah, you're right. I think for a lot of games you can deal with cheaters in that manner. But the games that we build are quite deep in level, in kind of complexity, and actually most of it is kind of authoritative in terms of we can stop a lot of these things, but it's an incredibly deep problem, and to the point where there are always going to be some ways in which people can find ways around it. And also, as I said, it's an arms race. There's people that are legitimately like spending days trying to find out how they can come and get around our system. Go on.
So I guess here, I was wondering if you considered it. You remove the step function with the 10 and the math, and then because differentiation sucks.
Yeah.
But in that space, one can imagine that clusters at some point do appear.
That is true. Yes, that is.
One can imagine, isn't that maybe the feasible route? Because then you can still do the clustering, and then also you get confirmation that clusters indeed exist.
Yes, you're right, and that is definitely a way we could go around it. I don't think that was really going to necessarily solve our problem here, though, because in essence, if we find clusters in our data, then they are a player behavior that is probably quite normal, and not everybody plays the game exactly the same, and so actually what we're trying to find is the people that don't fit into clusters of our data. Yeah. Has that answered your question?
Yeah, so I was thinking maybe suppose you had like clusters there and someone was not in one of those clusters, that might be a red signal, but you get the same thing, I guess, from just seeing the difference.
So now you're catching and banning cheaters. How does that affect the company's profit margin? Does it increase the conversion rate? Does it reduce resource costs? Or
so the biggest thing is over resource costs mainly. So for a while we had a big team having to deal with a lot of a huge manual process to do this. And what we've done is kind of found ways to completely automate that and take that away from them. So it's a resource cost, and also it's just kind of consumer-facing kind of. I think what you're saying is like, what's the bottom line metric that we've improved? The revenues. There's probably an implicit increase in revenue given the fact that people aren't perceiving cheaters in our game anymore and therefore not playing. But the one kind of metric that we were trying to do is just kind of the amount of complaints of cheaters that we were having. Can we reduce that? And we reduced that by, vast amounts. So, yeah. Sorry.
Have you looked into having a ground truth vision of what makes a cheater, and not focus on, let's say, replicating neural nets, but more based on historical facts or based on previous evidence that this guy's a cheater based on these certain features, let's say.
Yeah.
Have you looked into that, forcing a supervised learning approach?
Yeah, so that's kind of, I didn't really go much into it, I kind of touched on it at the end, is once we have that ground truth, that's kind of what we did. But the problem being, right at the start, is we don't have that view. And so we need ways in which to be able to filter through kind of what could be a cheater, what couldn't be a cheater, so that we can then go and check and analyze that data.
And a follow-up question to this, how do you manage, because the data is going to be very skewed, right? You're going to have 1% cheaters and 99%. How do you manage that when you train your classifier?
So this is back to here. So what we're doing is using the outlier score to resample the data such that we actually have more of, we have more cheaters or more outliers in our data that when we go and find the ground truth will therefore have a larger amount of things. So it kind of deals with that class imbalance.
You mentioned a whale and a cheetah look very similar in the behavior of their attributes, and it seems like a big issue is ruining every other user's experience by these over-leveled, really strong players killing it for them.
Yeah.
Do they have any way to be able to tell if someone's spending or cheating, and by that, is not kind of an implicit thing that big spenders, what's really good for you, can then affect the game as a whole because they're killing the community?
There's definitely a slight issue with that. Because they look so similar, people can perceive cheating when actually there's just people who are very, very active in our game and kind of high level. So that's kind of a slightly different problem. It's more like structurally, how do we build the game such that everyone can enjoy it? There was another point, sorry, what was the other point to the question?
I guess it's answered by you've done to game structure, but just not ruining the user experience if they can't identify a spender versus a user.
That was it, the identification. So, I mean, that's definitely an approach we can do. We can have a feature that kind of badges VIPs, but as a VIP, do I want to tell people how much I've spent in this game? It's not necessarily, that's not necessarily something that you'd probably want to see be showing as somebody who has kind of spent some money in that game. So it's a very, very tough one, and that player perception thing is a completely different problem of, once we believe we've actually solved the problem, there's still that level of somebody thinking that there's cheating going on when actually they're just seeing kind of very, very active players playing the game. Yeah.
Apologies if you've covered it already, but if you have a hypothesis about what a cheater looks like, what was the reason why you're not manually labeling some cheaters and then training the data set to find others like them?
So you're saying, so why did we not just have labels straight away? Because we would end up having users that we've already found before this method that we know as cheaters. The problem is we only have one label there. We don't have the opposite to it, because then we just have a pool of people that we think aren't cheating, but they could potentially be. It's one of those things that it's similar to the problem we had with the game and the fact that we didn't end up building a classifier, because we had ground truth that we could attribute as these are the exact ways that people are cheating. And so if we just tried to approximate and build a classifier that approximated those ground truths, it would never be as good as the ground truth itself. But there is that other, and we're kind of then also missing the extra level of the cheating we don't know about. And so that's why we kind of went through this method of just fully understanding the outliers in our game to fully understand all of the different vectors of cheating.
So this step from having outliers to having ground truth set, that's still manual?
Yeah, that is still manual, unfortunately. I mean, but it's worthwhile as well, because we've now taken a statistical view of this. Now we need a real game view of why people are doing this, and that's not just affected cheating, but it's affected kind of how we've built our game going forward, because we now understand not just how cheaters are cheating, but how our kind of high-level players are also playing and what the differences are. Yeah.
So how big of a problem is actually in the gaming industry? If you can say what percentage actually of players are cheaters, I don't know if you're allowed to say this.
No. So it can be a problem, and it's definitely a problem amongst these kind of deeper level games, because people will spend a lot more, and definitely on a social level it's a huge problem, because even if you have a small amount of cheaters, they can cause a lot of negative feelings for all of the legitimate players in your game. But in terms of, it's not necessarily a fact of whether you've got a high problem with cheating or a low problem. Any problem with cheating is a huge problem, because it's in social games it's going to affect those legitimate players. Is there any? Yeah.
Thanks for it. Really interesting topic. So I didn't quite understand how you measured that the replicator neural net was better than the previous method, and how did you make sure that you mitigated the risk you mentioned might appear previously? For example, that people that spend a lot are also outliers, or that you want some robust. In the previous methodology, there was a statistical way to make sure that your ellipsoid was robust. Whereas, how do you make sure that you get the same sort of result and better using the neural net?
That's a very good point. So are you saying how? Can I just rephrase the question a little bit? Are you saying how did we know that replicator neural net was better than the distribution-based methods?
As one, and then how do you make sure you mitigate some of the concerns you had in the previous slide, which were that you want to kind of reduce the variance, you want to kind of create a circuit that is robust, and it's not an outlier doesn't create an artifact.
Okay, so the first question on the kind of replicator neural net is it kind of there's no one way to do this. It's not a very simple mechanism of just having a value and making sure it's minimized for the right model. What we actually found is we actually used a distribution-based method on the first of our games that we did this with. And that was implemented, but we learned a lot from it and realized that there was certain areas that we needed to address in the way that we calculated the outliers. So when we went to the neural net, we kind of made sure that it was as good as in terms of the things that it was doing well, and it was actually taking care of the problems that we'd seen in the first implementation. So it was a very, very, that's quite subjective, isn't it?
But did you have a data set of cases of things that you wanted to kind of make sure that the neural net is capturing? So you had a data set and a metric around that, and make, or was it an empirical approach?
It was kind of, yeah, it was a relatively subjective approach. What we found is it seemed to differentiate true outliers a lot better. But that, yeah, generally it was quite a subjective approach. And the second one was based on the distributions.
Yes, how do you make sure that the neural net essentially is mitigating the concerns you raised in the previous slide?
So again, this was kind of an implicit assumption, but we knew it would hold, is there are very, very particular things that your data needs to be for the distributions to work. Whereas actually on the neural net, we knew that we wouldn't have to worry as much of those at those points. But again, it comes back to the same thing. We knew, having implemented it, the problems that we'd found and the reasoning, because of some of our data wasn't actually, we weren't able to bring it into a kind of Gaussian unimodal space. We were then able to check that once we implemented the replicator neural net, that those problems no longer arise.
Okay, there's no more questions. Let's.
Cool, thank you.